Okay. All right. So we are looking at chlorine gas at negative 13.5 degrees Celsius, and we're looking for the pressure. Come on, focus up. There we go. Cool. And we're given the Clausius-Clapeyron equation, which has the ln of P1 over P2 is equal to the delta H of vaporization, divided by R, 1 over T, I always get these mixed up, T2 first. And then we're given a table with information. Chlorine is there. So we're given the enthalpy of vaporization is 20.71. Yeah. Oh, 0.41 kilojoules per mole. And the boiling point is 239 Kelvin, right? And then you were also told that to assume that the boiling points that were given were the normal boiling points, right? What does that mean, the normal boiling point?
It's at 1 atm.
Exactly. So P1 is 1 atmosphere, okay? Everybody still okay with me? Cool. Yes. So we're looking for P2 here. So we can plug in all our other guys. Now, important here, this guy needs to be in joules, not kilojoules, right? Because this version of R that we're using is joules per mole Kelvin, right? So we need to make sure that this guy is in joules per mole. Does that make sense, guys? We cool? Anybody?
I do not know where I went wrong, like, when solving this. I think, like, I didn't read the information correctly, like, on the table. I think it just, like, had a lot of stuff. That's where I mixed up, because I pretty much, like, wrote everything out, like, the T1, P1.
Okay. Yeah. So, but everything's making sense, is what I'm getting at.
Yes.
Cool. All right. And then we'll have 1 over T1 is going to be 273 minus 13.5, right? Minus 1 over 239. Right? All right, guys. So I need your help. Can you calculate this whole bad Larry for me? Sorry, guys.
negative 0.8114.
Anybody else? This is a bigger number. Yeah. Is everybody else just...
Yeah, I got that.
Okay, cool. All right, and then that's going to be equal to the ln of 1 ATM divided by P2. And so how do we get rid of a ln?
E.
Yeah, so we need to raise both sides to the E, right? And then we'll have 1 ATM over P2 is equal to E to the negative 0.814. I'm sorry, 114. Sorry. Meow. What you got?
Uh, 0.444.
Any units?
Not yet, right?
Not yet. So now we just have to rearrange to solve for P2, right? So we can multiply P2 over here and then divide 0.444 over on the other side, right? So we have P2 is equal to 1 ATM divided by 0.444. So P2 is equal to
2.25.
how are we doing with that, guys? So let's talk about whether or not this makes sense, right? So at a lower temperature, the vapor pressure is higher. Does that make sense? Why, Harrison?
Yeah, I was gonna say, wouldn't it be lower? I'm kind of confused now.
That's okay. Okay, so thinking about the vapor pressure, right? This is the amount of the liquid that would exist in a vapor above the liquid, right? And we said that if the temperature increases, what happens to the vapor pressure?
It increases.
It increases, right? So if the temperature is decreasing, then should our P2 be
Higher? No.
higher? No. So that's problematic.
As in, like, we did the problem wrong, or as in the...
I'm going to have to do the calculation on my own, but that does not look good to me. Does it make sense why, though?
Yeah, definitely. And that's why I was kind of struggling with, on, like, the homework problem, too.
Yeah.
I ran into the same situation where, like, so I basically had the same thing as you, where I had, my unit list number on the right was the same, but because I switched what I had as my P1 and P2, I had it as P2 over 1 ATM.
Which would make it make a lot more sense.
Yeah. But also there's like a short version of the equation when you're looking for P2, where it's like e to the power of like delta H times 1 over T2 minus T1. And I was
I
just
think I know what you're
thinking that-
talking about. Okay, well, let me look at this problem because I have to go through the math. But if the math is correct here, then you guys are right. Right? It doesn't mean that we did the problem right, but it means that I might have given you guys. Let me get this. Oh. Boop.